Hello, and welcome to General Astronomy, Lecture 12, Geology of the Terrestrial Worlds. The familiar face of the full moon reveals some of the surface distinctions that we've already discussed. The bright, heavily cratered regions are the lunar highlands. The smooth, dark regions are the lunar maria, which got their name because they look much like oceans when seen from afar. Maria, which stated singularly is mar, is Latin for seas. But the entire surface of the moon should have been packed with craters during heavy bombardment. So what happened to the craters that must have once been located in the regions where we now see those dark maria? Right, so reason should have it that the whole surface should be roughly equally cratered, but we see that these dark patches hardly have any craters. So from what we've learned in our previous lectures, we should have a hint as to what may have caused that, but we'll talk about it now. Well, during the heavy bombardment, craters covered the moon's entire surface. The largest impacts were violent enough to fracture the moon's lithosphere beneath the huge craters that they created. However, the moon's interior had already cooled since its formation, so there was no molten rock to flood these craters immediately. Instead, the lava floods came hundreds of millions of years later, thanks to heating released by the decay of radioactive elements in the moon's interior. This heat gradually built up during the moon's early history until the mantle material melted between about 3 and 4 billion years ago. Molten rock then welled up through the cracks in the lithosphere, flooding the largest impact craters with lava. The maria are generally circular because they are essentially flooded craters, and as we learned, craters are almost always mostly round. Their dark color comes from the dense iron-rich rock, which is typically basalt, that rose up from the lunar mantle as molten lava. The flat surfaces of the maria tell us that the lunar lava spread easily and far, which means that it must have been among the runniest lava in the solar system. Right? So thicker lava builds up in the place where it spews from, whereas runny lava can fill this entire crater. On the whole, the maria have fewer craters than the surrounding terrain. Craters are caused by meteoric bombardment, so the maria must not have been exposed to that bombardment for as long as the surrounding terrain. Hence, the maria must be relatively young, and the lava flows that formed from them must have occurred at later stages in the moon's geological history. So these series of images here on the bottom just shows you that process. So early on, the moon's entire surface was heavily cratered, but then you might have had a big impactor come in that eventually allowed magma to rise and flow into the crater as lava, and since it was runny lava, it was able to fill up the entire crater, and then it solidifies into this rocky plain. And that's what you see in these dark regions on the moon. The moon's relatively few tectonic features are also found within maria. These features, which look much like surface wrinkles, probably were created by small-scale tectonic stresses that arose when the lava that flooded the maria cooled and contracted. A good analogy for these what we call scarps is the wrinkling seen on a fruit skin as the fruit dries out and contracts. And you can see great images of these scarps here. So we believe this is just the contracting of that new material. Remarkably, when the moon's far side was photographed for the first time by the Soviet Luna 3 spacecraft in 1959, scientists were surprised to find almost no maria there. Lunar highlands predominate on this side of the moon that faces away from the Earth. The crust is likely thicker on the far side, so even the most massive impacts were unable to crack through the crust and let lava flood onto the surface. The moon is not unique in having major portions with different crustal thicknesses. Earth's northern hemisphere has much more continental crust than the southern hemisphere, and the southern hemisphere of Mars has a thicker crust than the northern hemisphere. So this is not uncommon, but that can explain why there's hardly any maria on the far side of the moon. No evidence for plate tectonics can be found on the moon. It appears that the moon is a one-plate world. In other words, its entire lithosphere is a single solid plate. There are no rifts where plates are moving apart, no mountain ranges of the sort formed by collisions between plates, and also no subduction zones. All things we'll talk about more when we discuss the Earth's geology in our next video. Geologically, we consider the moon to be dead. In other words, we say it's geologically dead. Without an atmosphere to cause erosion and without plate tectonics, the surface of the moon changes only very slowly. This is why the moon's craters, many of which are now known to be billions of years old, remain visible today. The Apollo astronauts set up 4 seismometers on the moon's surface, which made it possible for scientists to investigate the moon's interior using seismic waves. The moon exhibits far less seismic activity than the Earth. Roughly 3,000 moonquakes were detected per year, whereas a similar seismometer on Earth would record hundreds of thousands per year. Furthermore, typical moonquakes are very weak. A major terrestrial earthquake is on the range from 6 to 8 on the Richter scale, while major moonquakes measure 0.5 to 1.5 on the scale and would go unnoticed by a person standing near the epicenter. Analysis of moonquakes reveals that the moon has a thick mantle surrounding an iron-rich core. The moon also has a crust with an average thickness of about 60 kilometers on the Earth-facing side and 100 kilometers on the far side. So again, more direct proof that the two sides of the moon do have different thicknesses. For comparison, the thickness of Earth's crust ranges anywhere from 5 kilometers, which is that's under the ocean floor, to about 70 kilometers under major mountain ranges. And this image just shows you the general structure of what the interior of the moon would look like. So a very large mantle and then a core in the center. More than 30 years after the original Apollo data revealed a molten core, I said that in a weird way. So let me rephrase it. More than 30 years after the original Apollo data, a molten core was revealed. Like Earth, the moon's iron-rich core had a solid inner core, surrounded by a liquid outer core. However, the liquid core is too small for the convection that is needed to generate a global magnetic field. On the whole, seismic waves indicate that the moon's interior is much more rigid and less fluid than the interior of the Earth. Plate tectonics requires that there be fluid motion just below a planet's surface, so it is not surprising that there is no evidence for plate tectonics on the lunar surface. Earthquakes tend to occur at the boundaries between tectonic plates. Where plates move past one another, they collide and undergo subduction. But there are no plates on the moon. So then a good question would be, well, what's causing those moonquakes? Even though there's not a lot of them and they're weak, well, what causes them if we don't have those plate tectonics? Well, in this case, it actually is caused by the Earth, and it's the Earth's tidal forces that are affecting the moon. So just as the tidal forces of the sun and moon deform Earth's oceans and give rise to ocean tides, Earth's tidal forces deform the solid body of the moon. And as a result, the moon flexes slightly, and that triggers those moonquakes. So the Earth is quite a bit bigger than the moon, so we have a pretty good gravitational pull on it. So the tidal forces, by us being near one another, actually allows the Earth to slightly flex the surface of the moon, and even that slight flexing causes those weak moonquakes. So now we can go into a discussion of where the moon actually came from. Well, we have something that's called the collisional ejection theory. This proposes that the proto-Earth was struck off-center by a Mars-sized object about 4.5 billion years ago, and this collision ejected debris from which the moon formed. The collisional ejection theory agrees with what we know about the early history of the solar system. We saw previously that smaller objects collided and fused together to form inner planets. Some of these collisions must have been quite spectacular, especially near the end of planet formation, when most of the mass of the inner solar system was contained within a few dozen large protoplanets. This theory proposed that one such object, a Mars-sized protoplanet, struck the proto-Earth about 4.5 billion years ago. So this figure shows the result of a supercomputer simulation of this cataclysmic event. In the simulation, energy released during the collision produces a huge plume of vaporized rock that shoots out from the point of impact. As this material is ejected, it also cools and then coalesced to form the moon. So here you see the impactor striking the Earth, it ejects that material, and then that material starts to orbit the Earth, and as it does so, it starts to cool, and then we get our moon. So that is the leading theory for our moon's origin. This theory also agrees with many properties of lunar rocks and of the moon as a whole. For example, rock vaporized by the impact would have been depleted of volatile elements and water, leaving the moon rocks that we now know. If the off-center collision took place after differentiation had occurred on Earth, where, again, the heavier elements sink to the center, after that had occurred, so that our planet's iron had sunk to its center, then relatively little iron would have been ejected to become part of the moon. Right? So if our Earth had differentiated and all the heavy stuff went to the center, and then something came and struck the surface material off, we wouldn't expect that heavier material to be out there for the moon to form. And the lack of iron on Earth's surface explains the moon's low density and the small size of its iron core. So this theory does match a lot of our observations, which is why it is our leading theory today. There are other theories, but none of them are as widely accepted as this one. So what I have here is just a quick 40-second simulation video. There's no music or sound, and I probably won't talk much at all during it, but this just shows a supercomputer simulation of what this formation might have looked like. So you can see that impactor, and they're using some particle simulations here, and you can see how that material will group up. And I believe the color indicates temperature, where the darker reds are the warmest, and then the yellows are cooler. So you can see how this material begins to orbit the proto-Earth. And in this simulation, you don't actually see the moon form, but you get to see at least what the impactor looked like, and then you can get an idea of how the moon could form. So over a long time, all these orbiting particles might either fall to the proto-Earth or coalesce into the moon. So that gives you a nice idea of what this might have looked like. Alright, well, that's enough for the moon. Let's move on to another body in our solar system, the first planet we'll discuss the geology of. And I put the moon first because our next planet that we come to, which is Mercury, has a very similar look. In fact, the Mercury looks so much like the moon that it's often difficult to tell which world you are looking at surface photos. Nevertheless, the two worlds do have a few important differences. Impact craters are visible almost everywhere on Mercury, indicating an ancient surface. However, Mercury's craters are less crowded together than the craters in the most ancient regions of the moon, suggesting that molten lava later covered up some of the craters that formed on Mercury during heavy bombardment. As on the moon, these lava flows probably occurred when heat from radioactive decay accumulated enough to melt part of the mantle. Although we have not found evidence of lava flows as large as those that created the lunar Maria, the lesser crater crowding and the many smaller lava plains suggest that Mercury had as much volcanism as the moon. The largest surface features on Mercury are huge impact craters called basins. These impacts were so large and so violent that the craters filled with molten rock heated by the impact. For example, the Chloris Basin spans more than half of Mercury's radius. Many of these basins have few craters within them, indicating that they must have formed at a time when the heavy bombardment was already subsiding. The most surprising feature of Mercury is that it has many tremendous cliffs, evidence of a type of tectonics quite different from anything we have found on any of the other terrestrial worlds. Mercury's cliffs have vertical faces of up to 3 or more kilometers high, and typically run for hundreds of kilometers across the surface. So you can actually see one of them right here. This thing is massive. They probably formed when tectonic forces compressed the crust, causing the surface to crumple. Because crumpling would have shrunk the portions of the surface it affected, Mercury as a whole could not have stayed the same size unless other parts of the surface expanded. However, we find no evidence of similar global scale stretch marks on Mercury. So could the planet as a whole have shrunk? Well, apparently so. In addition to being larger than the moon, Mercury also has a surprisingly large iron core. Mercury therefore gained and retained much more internal heat from accretion and differentiation than the Moon did. This heat caused Mercury's core to swell in size. So later, as the core cooled, it contracted by perhaps as much as 20 kilometers in radius. The mantle and lithosphere must have contracted along with the core, generating the tectonic stresses that created these great cliffs. The contraction probably also closed off any remaining volcanic vents, which then ended Mercury's period of volcanism. So we now also say that Mercury is a geologically dead world. Compared to Earth's core, Mercury's iron-rich core takes up a much larger fraction of the planet's volume. Indeed, Mercury is the most iron-rich planet in the solar system. The iron core covers about 83% of its radius and 68% of its overall volume, whereas Earth's core is only 55% of its radius and 17% of its volume. So you can get a sense of how impressive these actually are. Well, several theories have been proposed to account for Mercury's high iron content. So according to one theory, the inner regions of the primordial solar nebula were so warm that only these substances with the higher condensation temperatures, such as iron-rich materials, could have condensed into solids. But another theory suggests that a brief episode of very powerful solar winds could have stripped Mercury of its low-density mantle shortly after the Sun formed. So those are two theories. But as far as I know, right now, the leading theory is one that deals with an impactor. A third possibility is that during the final stages of planet formation, Mercury was struck by a large planetesimal. Supercomputer simulations show that this cataclysmic collision could have ejected much of the lighter mantle, leaving a disproportionate amount of iron-rich material to reaccumulate and form the planet that we see today. So that's what this snapshot of a simulation is showing you. You've got proto-Mercury and then a planetesimal smashing directly into the planet. Well, that will blast the outer layers of the planet, seen here in blue, away from the two objects that just collided. So then Mercury will reform from the iron-rich material that's left over. Right? So everything else gets blasted away into space, but what's left over is mostly the iron-rich material that's stuck here in the center. So that's the main theory as far as I know. All right, well, on to Mars, the next largest object in our solar system. Aside from the polar caps, the most striking feature of Mars is the dramatic difference in terrain around different parts of its surface. Much of the southern hemisphere has relatively high elevation and is scarred by numerous large impact craters, including the very large crater known as the Hellas Basin, which you can see right here. In contrast, the northern plains tend to be below the average Martian surface level and show few impact craters. The difference in cratering tells us that the southern highlands are an older surface than the northern plains, which must have had their early craters erased by other geological processes. So let's talk about some of those. Volcanism was the most important process in erasing craters on the northern plains, although tectonics and erosion also played a part. However, no one knows why volcanism affected the northern plains so much more than the southern highlands, or why the two regions differ so much in elevation. More dramatic evidence of volcanism on Mars comes from several towering shield volcanoes. One of these, Olympus Mons, is actually the tallest known volcano in the entire solar system. Its base is some 600 kilometers across, which is large enough to cover in the entire state of Arizona. Its peak stands about 26 kilometers above the average Martian surface, or about 3 times as high as Mount Everest stands at above sea level on Earth. And then it is rimmed off by a cliff that places it 6 kilometers high. So this is Olympus Mons, an image of it, and here is just a quick schematic to show you just how massive this thing is. Here's Mount Everest, the largest mountain range on Earth, and it pales in comparison to Olympus Mons, this single volcano on the Martian surface. So it's a very impressive feature. Olympus Mons and several other large volcanoes are concentrated on or near the continent-sized Tharsis Bulge, which I'll go back for a second. You can see right here. So here's that central region of that bulge, and here's Olympus Mons. So they're centered on the Tharsis Bulge, which is some 4,000 kilometers across, and most of it rises several kilometers above the average surface level on Mars. It was probably created by a long-lived plume of rising mantle that bulged the surface upward and provided the molten rock for the eruptions that built those giant volcanoes. We expect Mars to be much less volcanically active than Earth, because it is smaller in size and has allowed its interior to cool much more. Plus, the Martian volcanoes showed enough impact craters on their slopes to suggest that they have been inactive for at least tens of millions of years. However, geologically speaking, tens of millions of years is not that long. In addition, radiometric dating of meteorites that appear to have come from Mars shows some of them to be made of volcanic rock that solidified from molten lava as little as 180 million years ago, quite recent in the 412 billion year history of the solar system. Given this evidence of geological activity recently, it is likely that Martian volcanoes will erupt again someday. In addition, scientists suspect that the presence of methane in the Martian atmosphere suggests that it might also point to ongoing volcanic activity right now. Nevertheless, the Martian interior is presumably cooling and its lithosphere is thickening. Within a few billion more years, Mars will become as geologically dead as the Moon and Mercury. All right, on to tectonics. Well, Mars also has tectonic features, though none on a global scale like the plate tectonics of Earth. The most prominent tectonic feature is the long, deep system of valleys called the Valles Marineris, named for the Mariner 9 spacecraft that first imaged it. Valles Marineris extends almost a fifth of the way across the planet's equator. It is as large as the United States is wide and almost 4 times as deep as Earth's Grand Canyon. No one knows exactly how it formed. So again, just to show you some comparisons, here's an image of it, the canyon, or the valley, and here is its size comparison to the United States, and its size comparison to the Grand Canyon. So if you've ever seen images of the Grand Canyon or been there yourself, you know it's just an incredibly huge and just impressive feature. Well, it looks like a little pothole compared to this trench on Mars. So it's quite an impressive thing. So parts of this canyon are completely enclosed by high cliffs on all sides, so neither flowing lava nor water could have been responsible. However, extensive cracks on its western end run up against that Tharsis bulge, suggesting a connection between the two features. So I'll go back again even. So here is the trench, and then here is that Tharsis bulge. So perhaps it formed through tectonic stresses accompanying the uplift that created that bulge, cracking the surface and leaving the tall, walled-off cliffs that we see. So they could be connected. Well, impacts, volcanism, and tectonics explain most of the major geological features on Mars, but closer examination shows the extensive evidence of erosion by liquid water as well. For example, the figures here show what appear to be dried-up riverbeds that were almost certainly carved by running water, although we cannot yet say whether water came from runoff after rainfall, from erosion by water-ice debris flows, or from an underground source. Regardless of the specific mechanism, water is the only substance that could have been liquid under past Martian conditions, and that is sufficiently abundant enough to have created such extensive erosion features. We must therefore look more carefully at the evidence suggesting that Mars once had abundant surface water. Current surface conditions do not necessarily allow for liquid water to remain stable on Mars. In most places and at most times, Mars is so cold that any liquid water would immediately freeze into ice. Even when the temperature rises above freezing, as it often does at midday near the equator, the air pressure is so low that liquid water would quickly evaporate. If you put on a spacesuit and took a cup of water outside, your pressurized spaceship, if you took it outside of your pressurized spaceship, the water would rapidly either freeze or boil away, or some combination of both. When we combine the clear evidence of water erosion with the fact that liquid water is unstable on Mars today, we conclude that Mars must have once had a very different surface condition, that is, conditions such as warmer temperatures and greater air pressure that would have allowed for water to form and for rain to fall. Geological evidence indicates that warmer and wetter periods must have ended long ago. Strong evidence that Mars had rain and surface water in the distant past comes from both orbital and surface studies. The figure here shows a broad region of the ancient, heavily cratered southern highlands. Notice the indistinct rims of many of the large craters and the relative lack of small craters. Both facts argue for ancient rainfall, which would have eroded the crater rims and erased the smaller ones altogether. So this figure shows what looks like a river delta that is on the bottom. So this is what it looks like on Mars. That's a real image from Mars. This one's from Earth. Definitely not Mars. That'd be impressive. But this figure shows what it would look, or what looks like a river delta where water flowed into an ancient crater. Further evidence that the crater was once a lake comes from images and spectra indicating the presence of clay materials on the crater floor, presumably deposited by sediments flowing down the river. So I just threw in this image here at the top to show you what a river delta looks like on Earth, and you can kind of see the distinct similarity between them. I mean, you've got a river coming in that spreads out into this delta. Some studies even suggest that the northern plains may have once held a vast ocean, though the evidence is less definitive than the evidence for smaller lakes. The evidence for the ocean comes from features that look like an ancient shoreline, along with data suggesting that the rocks along the proposed shoreline is sedimentary rather than volcanic, just as we would expect if there had once been an ocean. This rock may even contain water ice in its pores and cracks. Surface studies further strengthen the case for past water. In 2004, the robotic rovers Spirit and Opportunity landed on opposite sides of Mars. Spirit landed in the Gusev crater, the site of a possible ancient lake, and Opportunity landed in the Meridian plains, where orbital spacecraft had detected spectroscopic hints of minerals that formed in water. The rovers carried cameras, instruments to identify rock composition, and a grinder to expose fresh rock for analysis. The rovers long outlasted their design lifetime of 3 months, with Spirit lasting more than 6 years and Opportunity still going as this textbook was written, more than 8 years after arrival. So this book was written just a few years ago, and I believe Opportunity is still going today, though its wheels are all carved up and everything from the harsh environment. The rovers provided clinching evidence through identification of several minerals known to form only in the presence of water. Immediately after landing, Opportunity found tiny spheres, nicknamed blueberries, that contained iron-rich minerals called hematite, and nearby rocks containing the sulfur-rich material drossite. So drossite is on the left, and those little blueberries we were talking about are on the right. So terrestrial examples of these minerals form in standing water or water seeping through rock. Detailed chemical analysis suggests that these minerals formed in a salty environment such as a sea or ocean. In 2012, after 20 miles of roving, Opportunity came across a mineral outcrop made of gypsum, another sulfur-rich mineral that only forms in water, and that's here on the bottom. You can see that. On Earth, it's the main ingredient in drywall building material. Opportunity team leaders called the discovery a slam dunk story that water flowed through underground features and rocks. Well, taken together, the orbital and surface studies provide convincing evidence for abundant liquid water in Mars's distant past. But could water have flowed more recently? Abundant water ice still remains on Mars at the polar caps and underground over much of the planet. Although this ice probably represents only a fraction of the water that once existed on Mars, it is still enough that if it all had melted, it could make an ocean about 10 meters deep over the entire planet. The atmospheric pressure on Mars is too low today for significant melting to occur on the surface, but it is possible that some liquid water exists underground and near sources of volcanic heat. If so, this liquid water could potentially provide a home for microscopic life. Moreover, if there is enough volcanic heat, ice might occasionally melt and flow along the surface, for a short time until it freezes over or evaporates. Although we have found no geological evidence to suggest that any large-scale water flows have occurred on Mars in the past billion years, orbital photographs offer tantalizing hints of smaller-scale water flows in much more recent times. The strongest evidence comes from photos of gullies on craters and channel walls. These gullies look strikingly similar to the gullies we see on almost any eroded slope on Earth. And spacecraft images show that new gullies are still forming. One hypothesis suggests that the gullies form when snow accumulates on the crater walls in the winter and then melts away from the base of the snowpack in the spring. So here's a steep cliff, and you see all these little gullies here. I mean, that looks exactly like if there was a muddy cliff on Earth and water running through it. If this hypothesis is correct, the water at the base could melt because of the angle of sunlight and the pressure of the overlying snow. The melting may have occurred during a time within the past million years or so when Mars's axis tilt was slightly different than it was today. Alternatively, the gullies may have been formed by landslides, which have been seen to occur elsewhere on Mars with the change of seasons. So there are other explanations. I mean, this does also look like a landslide, but this one to me looks, a lot more certain that it had something flowing. But, again, we don't know for sure just based on this. However, in these images, these dark, narrow 100-meter long streaks called recurring slopes lineae 100-meter long streaks called recurring slope lineae flowing downhill on Mars are inferred to have been formed by contemporary flowing water. Recently, planetary scientists detected hydrated salts on these slopes at Hale Crater, corroborating their original hypothesis that streaks are indeed formed by liquid water. And you can see that especially down here, these dark streaks. But something pretty recent and amazing. Here's an animated GIF of one of these regions. So these are taken about a month apart, March, April, and May. But notice that over these couple of months, you see the dark lines becoming much larger. So it certainly looks like we have flowing water. And this was the big deal when this was announced not too long ago, that there is pretty much visual evidence of at least some flowing water on the surface of Mars today. All right, one more planet before we stop and break and talk about the Earth. We have to talk about Venus. The surface of Venus is searing hot, with brutal pressure making it seem quite unlike the sister planet to Earth that it is sometimes called. However, beneath the surface, Venus and Earth must be quite similar. The two planets are nearly the same size. Venus is only about 5% smaller than the Earth in radius, and their similar densities suggest overall similar composition. We therefore expect the interiors of Venus and Earth to have the same structure and to retain about the same level of internal heat today. Nevertheless, we see ample evidence of skin-deep differences in surface geology. Venus's thick clouds cover much of the surface and prevent us from seeing through it with visible light. But we can study its geological features with radar because radio waves can pass through the clouds. Radar mapping bounces radio waves off the surface and uses the reflections to create a three-dimensional image of the surface. From 1990 to 1993, the Magellan spacecraft used radar to map Venus's surface with resolution good enough to permit identification of features as small as 100 meters across. Scientists have named most of the major geological features on Venus for goddesses and famous women. 3 elevated continents, or terra, are the largest of these surface features. So you can see those 3 terra labeled in the figure. The figure shows that Venus has many geological similarities to Earth. Like Earth, Venus has a relatively small number of impact craters, indicating that its ancient craters were erased by other geological processes. Moreover, while Venus has a few large craters, it lacks the small craters that are most common on other worlds, probably because the small objects that could make such craters burn up completely as they enter Venus's thick atmosphere. But even this thick atmosphere has little effect on objects large enough to create some of the largest craters that we see in the global view. Volcanism has clearly played an important role on Venus. Like Earth, Venus shows evidence for having had volcanic flows with a variety of lava types, since we see both lava plains and volcanic mountains. Some mountains are shield volcanoes, indicating an eruption with lava that was about as runny as that which was formed in the Hawaiian Islands on Earth. There are a few volcanoes, though, that have steeper sides, indicating eruptions with thicker lava. Venus almost certainly remains geologically active today, since it should still retain nearly as much internal heat as Earth. Although we have not witnessed any actual volcanic eruptions, at least two lines of evidence suggest recent activity. First, Venus's clouds contain sulfuric acid. Sulfuric acid is made from sulfur dioxide and water, and the sulfur dioxide must have entered the atmosphere through volcanic outgassing. Because sulfur dioxide is gradually removed from the atmosphere by chemical reactions with surface rocks, the existence of sulfuric acid clouds means that volcanic outgassing must have occurred within about the last 100 million years. The second line of evidence narrows the timescale even further. The European Space Agency, or the ESA, their Venus Express spacecraft, which orbited Venus since 2006, detected an infrared spectral feature on 3 volcanoes that suggested their rocks are fresh and erupted within the past 250,000 years or so. So you've got an infrared region, so we see the heat in that volcanic region. Okay, do I have... Interesting. I think I lost a slide on accident. So I'm just going to talk for this one real quick. I don't have a slide for it, but before we get to erosion, we have tectonics. I don't know why I lost that slide. I apologize. But tectonics has also been very important on Venus, as the entire surface appears to have been extensively contorted and fractured by tectonic forces. Some of these features, including the large circular corona, which is Latin for crowns, provide strong evidence for mantle convection beneath the lithosphere. The corona was probably pushed upward by hot rising plumes of rock in the mantle. The plumes probably also forced lava to the surface, which would explain why numerous volcanoes are found near it. So, at least a quick discussion on that before we get to erosion. We might naively expect Venus's thick atmosphere to produce strong erosion, but the view both from orbit and on the surface suggests otherwise. The former Soviet Union sent several landers to Venus in the 1970s and early 1980s. Before the intense surface heat destroyed them, the probes returned images of a bleak volcanic landscape with little evidence of erosion. We can trace the lack of erosion on Venus to 2 simple facts. First, Venus is far too hot for any type of rain or snow to occur on its surface. And second, as we have discussed, Venus's slow rotation means that there is very little surface wind, so there's no real way for any of this material to become eroded without any of that precipitation or wind. So I'll leave you here in this lecture video. The next one will be a little bit shorter. We're going to just discuss the unique geology of the Earth before we begin to discuss the atmospheres of these worlds. So as always, thanks for watching and take care.